Every quantum choice splits reality into two. This is not a metaphor. It is the most literal interpretation of quantum mechanics. This is the many worlds interpretation. Physics has a deep problem at its foundation. A quantum particle exists in superposition, spinning up and down simultaneously, existing here and there at the same time, until you look at it. The moment of observation destroys the superposition. One definite outcome appears. The question is, why? Why does observation collapse all those possibilities into one? The mathematics of quantum mechanics describes particles as waves of probability. Before measurement, the wave function spreads out, encoding every possible outcome. After measurement, it collapses to a single point. But here is the strange part. The Schrödinger equation, which governs quantum mechanics, has no collapse in it. The equation says superpositions evolve smoothly forever. Collapse was added by hand. As a rule, without physical explanation. For most of the 20th century, the standard answer was, do not ask. The Copenhagen interpretation says the wave function is a calculation tool, not reality. Measurement is the boundary between quantum and classical worlds. Do not ask what happens during collapse. Shut up and calculate. Most physicists accepted this. A graduate student named Hugh Everett did not. In 1957, Everett asked a simple question. What if the wave function never collapses? What if, instead of one outcome appearing, both outcomes always occur? When you measure a particle with spin up and spin down superposed, both outcomes happen. Both branches of reality continue. In one branch, you see spin up. In another branch, you see spin down. You have split. Both versions of you are real. Neither is a copy. This branching happens at every quantum event. Every radioactive decay. Every photon hitting every surface. Every electron in every atom. Each event spawns new branches. Trillions of times per second. Per particle, the universe multiplies. The total structure of reality is exponentially vast beyond imagination. Every possible history of every particle exists in full. The many worlds interpretation has one deep problem. In quantum mechanics, outcomes have probabilities. An electron has a 90% chance of spin up, 10% chance of spin down. But in many worlds, both outcomes happen. Both branches exist. So what does 90% mean? If both versions of you exist after the measurement, why do experiments confirm the Born rule probabilities? This is the deepest challenge MWI has not fully resolved. The other challenge is, why do we not see superpositions in everyday life? The answer is decoherence. Any quantum system that interacts with its environment loses quantum coherence rapidly. The quantum information leaks into billions of environmental particles. The branches become causally disconnected from each other. You cannot interact with the other branch. Not because it does not exist, but because the information has diffused beyond recovery. This is why quantum weirdness disappears at human scales. If many worlds is correct, the implications are extraordinary. There is no collapse, no special role for observers, no mystery about measurement. All possibilities are real, not probabilities of one outcome. You are constantly branching, with trillions of versions of you existing across branches. Each version is equally valid, equally you, none more real than the others. The universe is deterministic at the level of the wave function. The randomness you experience is just the question of which branch you happen to be in. Here is the uncomfortable truth. No interpretation of quantum mechanics is experimentally distinguishable from the others. Many worlds, Copenhagen, Bohmian mechanics, relational quantum mechanics, all predict identical experimental outcomes. The question of which is right is not a physics question. It is a question about ontology, about what exists. Copenhagen says, do not ask about reality. Many worlds says, ask. And the answer is more real than you imagined. All of this is real.